Well, it's my pleasure to introduce to you Lucas Schamber. He's going to talk about wireless measurements in space using RF tags and no power. Without further ado, Lucas.
All right. Thank you, Dr. Packard. As he said, my name is Lucas Schamber, and I am a member of the RIFSAT team, which I will get to in a bit. But basically, I'm going to be talking about my contribution to the project after explaining essentially what the project is. So just for a quick overview, I'm going to go over who RIFSAT is as the team, and then I'm going to talk about an overview of our project. I'm going to explain a little bit about RFID, which is the main technology that we're trying to demonstrate with this project. Then after that, I'd like to go over a risk assessment, mainly the one that I participated in, which was thermal analysis. Then I'll go over the payload, and then go into our conclusion and questions. So to start with RIFSAT. RIFSAT is a team of science and engineering majors, and we have been tasked with building a satellite. We got our funding through a NASA USIP grant, and USIP stands for Undergraduate, I'm blanking on that. It's Undergraduate Space Instrument Project, if I'm not mistaken. So from left to right, we have Brandon Pankey here, Daniel Slimmer, Curtis Garner, Cassie Wade, our team leader, there's me, and Jordan Poundstone. And my main goal, or my main purpose in this team is to be the physicist. So I'm the lone physicist. It's a bit like being the fifth Beatle. Okay, you gotta understand that. So it's been an interesting time. Naturally, the first question is, what is RIFSAT? Well, RIFSAT is a 3U CubeSat that we are currently developing here at NMU. For those of you who don't know, a CubeSat is a particular form factor for a very small satellite. And you'll see our engineering model up here in front, in fact. So a CubeSat is a 10 centimeter by 10 centimeter by 10 centimeter cube unit. And these units are stackable, so you can have 1U, 2U, 3U. In this case, ours is a 3U, as you can see, because it's 30 by 10 by 10. And RIFSAT stands for Radio Frequency Tag Satellite. And the reason for this is that we are going to demonstrate the use of energy harvesting RFID tags in space. We're expected to finish building around fall of 2017. Unfortunately, we have not yet determined the launch. So we're still looking, we're hoping. We really want that to happen soon. Naturally, the next question would be, what is RFID? It stands for Radio Frequency Identification, and these things are everywhere. They are what are in your cards that allow you access to the different rooms around the building. They're small devices that communicate with a reader using radio waves. As you can see, the tag will be pulsed by an antenna, which is connected to a reader, and that will be sent back to a computer. So the advantage of these is that they're very small, they're very compact, and they come in two different varieties. There's active tags, which have their own internal power supply, like a small battery, and then you have passive ones, which will actually take the energy from the reader signal, process it, use it to power on, modulate it, and then send it back to the reader. And this is really nice because you essentially don't need any batteries whatsoever on these tags. So these tags have numerous applications on Earth as it stands. They're used all the time in things like shipping, so you can track the packages. They're used to detect water levels in tanks. They're really anything you can think of to use them there. Now, our goal in this project is to show that these have potential applications in space environments. A couple examples of this would be, say, in a docking procedure. You could have a ship with an RFID tag on the front coming into dock with RFID tags, say, around the ring, and you can get position data from that, so you can know if you're in line correctly to dock, or if you're misaligned, you need to readjust, things like that. They're also very useful for debris tracking. As we know, there's a huge amount of space debris in the atmosphere, and by sticking tags on these pieces of debris, we can better track them and hopefully mitigate any damage to, say, satellites or space stations, things like that. And then the third one, application would be structural health monitoring. Now, this is really useful in situations where a spacewalk is not desirable, because you could beforehand plant tags on the outside of a ship and monitor the structural integrity of the ship. There's no need for a spacewalk. If something burns out, you don't have to run wires to this tag, so it's very easy to quickly add a new one. And this lack of a need for wires is very useful because, especially when taking sensitive field measurements, these wires can cause fields that will negatively impact the measurement that you're trying to take. So now I'd like to go over our mission overview. We have essentially three main things that we're trying to accomplish. We are performing a technology demonstration of these energy harvesting RF tags as a method of collecting scientific data in space. We want to obtain specifically space weather from these tags, and we want to process that and send it back to Earth via a radio network called Globalstar, which is a network of satellites in orbit over the Earth. Our minimum success criteria for this, number one, is essentially just to send the satellite up and get a ping back that says, hey, I'm here, I'm alive, I didn't blow up. That's baseline. Our second is to receive actual data from the tag and demonstrate that we can take sensor measurements with this RFID system. Our third goal is to receive sustained space weather data over the duration of the entire mission. This would be our ideal setup because we are actually getting to collect this scientific data that we want. Our fourth is to deploy the boom with the tag and read sensor data. I'll talk about the boom in just a little bit. And the number five is to deliver an image. This one is still kind of up in the air. We could put a camera on. We might not be able to. We are working to put it on if possible, but there might be some stipulations around that. So here you'll see our RIFSAT CAD model. And as you know, it looks very similar to our engineering model. You have your payload boards, which will go right here. These are essentially going to be processing the data. And it's also going to control the satellite itself. We have the EPS and the battery, which will sit right about here. And then that will connect to the simplex radio. And as you can see, we have two patches here. These were the two candidate positions for our antenna, and we decided to go with the sun. And here you will see our boom system. So we are actually going to be extending the tag out a long distance and measuring the data from the tag and sending it back to the receiver, which will be back on the main body of the satellite. Now I'd like to move on to risk assessment. One of the early concerns we had was with heat generation and thermal dissipation in space. As most of you probably know, heat is a serious concern in space because there's no atmosphere for conduction or convection. Every bit of heat that is released is done so through radiation. We needed a simple model for the temperature of the satellite in a worst case scenario. So I did what any good physicist would, and I made an equation. Pretty simple model. I took into account essentially that the power generated from the battery plus the incoming solar radiation would have to equal what's radiated through black body. So I just went ahead and solved this for the actual temperature as a function of emissivity and got this. And here's a chart explaining basically just what each of these values are and what value I chose to pick. So you will notice that the amount of energy coming from the sun is actually fairly minimal. You've got about 1,360 watts per meter squared, but you only have about 0.03 square meters of surface area for the large side of the satellite. And so really it's not as big of a consideration as you might think. Went ahead and plotted this in Excel. And as you can see, it drops down pretty dramatically as you approach emissivity 1. So what emissivity represents is essentially how reflective or absorbent, how much reflectance So something, say, for example, anodized aluminum. Anodized aluminum would have an emissivity of 0.77, and that would be higher for solar panels that we would have on the side of our satellite. And so what you can see is that because we're going to be dealing with emissivities in this area, we have no concern regarding the heat that this is producing, because all of our components are going to work well within that. Most of our components have cut off right at about 100. So as you can see, that's not going to be an issue in this case. Next, I'd like to get to the payload itself. What is it that we are measuring? So this tag that's extended on the boom will contain 3 sensors: a 9-axis inertial measurement unit, a thermal sensor, and an integrating dosimeter, which is just a radiation sensor. These thermal and radiation measurements will give us insight into the space weather related phenomena. And as you can see, this kind of illustrates how that backscatter system works. We've got this tag out here, it'll be pulsed, it will take its measurement, it will send it back in a modulated wave to the reader, which will then send it back down to Earth, to us through the Globalstar network. Once in orbit, the measurements will be taken without the boom extended first, and then after some time we will extend the boom and measurements from a distance will be taken. The satellite will then continue to send data until the system fails or it burns up. And our average mission lifetime will be anywhere from several months to several years, depending on what kind of orbit we get. As far as the sensors themselves go, the inertial measurement unit does kind of what you would expect it to do. It measures pitch, roll, and yaw with respect to the nadir angle, which is the angle pointing down to Earth. The temperature sensor obviously measures temperature. And then the integrating dosimeter measures cumulative radiation that the tag is exposed to. So as it encounters more radiation, it will go up and up over time. And essentially what's happening is that the radiation is bombarding the sensor, and it's causing the voltage to change. And so you can see that as the lifetime continues on. This is a really nice sensor because it's completely passive. It doesn't have to be powered on to work. The bombardments will happen, the voltage will change, and then we just take the measurement. So in conclusion, our development of our satellite is coming along nicely. Significant progress is being made. We're not done yet. This turned out to be a much bigger undertaking than I think a lot of us could have ever imagined, but it's definitely been rewarding. The risk assessment of the thermal model yielded no cause for concern. And the RF tag and reader systems should arrive soon, and the system integration will begin at that point. I'd like to thank the rest of my NURIFSAT team, the propagation group at Georgia Tech, who is actually building our reader system, and the NASA undergraduate student instrument project working with SIP grant. Questions?
So you said the dosimeter measured radiation, that's not from the RFID system itself?
No,
Okay.
that's solar radiation.
Okay.
Yes.
Can you go back to your sensor? So you mentioned that your dosimeter is passive. I'm assuming that your inertial and your temperature are active, so you need to power on.
That's correct.
Okay, so will those be local power supplies, or will they be?
All that power is coming from the RFID unit itself.
Okay.
So it's coming from that backside. Yes. So basically, as it powers on, it'll take the and so we'll have to also make it.
So your thermal analysis, you said you're pretty much expecting the whole outside of the satellite to stabilize for a very high emissivity. You know, you said you're assuming what, aluminum?
Anodized aluminum is about 0.77. We will have solar panels covering the satellite. Those will be even higher.
Our solar panels black. So normally, I maybe get this backwards. Really shiny things have
Very
low emissivity.
Yes.
Really dark things have high emissivity.
Yes, that's
Black body radiators have one.
Yeah,
Yeah.
it's a value of one, so it
So you're saying that if you use that's based upon an entire surface area of anti-slip.
Yes.
So
Again.
by throwing the solar panels on, you're actually going to be, that's a very conservative answer.
Yes.
Okay.
Yeah. And again, this is a very preliminary sort of model, but it gave us enough confidence to essentially move forward and say that this is going to be a major risk factor in our project.
For your dosimeter,
Uh-huh.
could you elaborate on more on how it's actually being changed so that it's passive and you can just take a reading off of it? Is it a material change that's making more resistant?
Yes.
or-
Yes. So as it's bombarded, essentially the resistance, it's essentially acting like a resistor in a lot of ways, but that resistance is going up as well. Yes.
So, I know this is mostly an engineering project, but you're gathering this data from the science part. What do you hope to learn from the measurements that we get?
Ideally, it would be great to get any kind of space weather data, but we will have a very accurate temperature model. We'll have this cumulative radiation dosing. I think it'll be interesting to compare the two and see if there's sort of a correlation between, or to look at if there are big spikes over certain parts of the globe or at different times, and just be able to compare these two existing models.
Well, that about wraps it up. Let's thank